Welcome back, everybody. This is our fifth session in JEE mains previous year questions for electromagnetic induction of class 12th. Before this video, we have made four videos in this series, and all of those videos are available on our YouTube channel in the playlist section. We have also started a similar series for NEET previous years. So if some of your friends are preparing for NEET, then you can guide them through those videos. And if you like these videos, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In the previous one, we completed around 20, I think. Let me check. So this was the last question which we completed, question number 21, and now we will start with question number 22. So let me adjust the thickness. So two coils X and Y are kept in a close vicinity of each other. When varying current IT flows through coil X, the induced EMF in coil Y varies in a manner shown here. Variation of IT with time can be represented by the graph as shown. So, okay, so we have been given induced EMF. We have been given induced EMF, and we have to find the actual current through which, due to flow of which, this EMF is induced. So let's slide it down slightly. Now, suppose we had a I current flowing. We have two coils, coil X and coil Y. Now in Y we have an induced EMF, and in X we have some current. Now suppose value of current flowing in the X is IT. Now due to this current, the induced EMF will be given by this relation. Induced EMF in Y, that will be equal to, so suppose Vt negative of d by dt of the flux associated with Y. This is the amount of induced EMF in the Y. Now, flux induced in Y will depend upon the magnetic field at Y, into area of the Y or coil Y, because both of these are coils. Now, area of the coil is constant. Here, magnetic field will be changing. Why? Because magnetic field due to a coil, suppose magnetic field at Y is equal to magnetic field at the center of the X. So magnetic field at a center of the X will be given by, we are just assuming that magnetic field at the center of X is equal to magnetic field at the center of the Y, so that we can take simpler expression. Or if they are some like this, suppose this is our coil X and this is coil Y, and they are coaxial, even in that case magnetic field will be mu naught by 4 pi into 2m divided by the distance of cube, that is r cube, and this magnetic dipole moment is again proportional to current. So here we will have, let's take this formula. It will be mu naught 4 pi 2m by r cube. R is the distance between these two coils, into area of the Y coil. Now here mu naught by 4 pi is constant, R is constant, 2 is constant, area of the that second coil is also constant. So we can say that Vt is equal to negative times some constant, that is C, into di by dt, where this I is the current flowing in the coil X, which is producing magnetic field at the center of coil Y. So that's this is our basic relation. Now come to this graph. We can divide this graph into three parts. This is region 1, this is region 2, and this is region 3. Now in the first region, we can say our potential is increasing and positive. Induced EMF is positive and increasing. What does it does mean? That di by dt should be negative here. So rate of change of current should be negative. Or we can say in the region 1, our current should be decreasing. Our current should be decreasing. Now coming to the region 2, here potential is decreasing. Potential is decreasing but still positive. Potential is decreasing but still positive. So it means again di by dt is negative, but the amount of di by dt or magnitude is smaller as compared to the previous one. And now going to the region 3rd, here potential is constant and negative. And potential is constant and negative, it means di by dt should be positive. In the third region, di by dt should be positive and should be constant, because here our induced EMF is also constant. And if we know that if we have some constant, di by dt is constant, it means that relation between or graph between I versus t will be a straight line. In the region 3, it will be a straight line, as if we derivate this, we will get a constant value. So in the first region, current should be decreasing, and in the third region, current should be increasing at a linear rate. In the first region, it will follow a curve. So in the option C, we can see here that here current is getting constant. If current is getting constant here, then EMF will reduce to 0, and that is not the case for a long time. So option C is rejected. Similarly, option D is rejected. Now coming to option A and B, that which one of these will be the right option. Now, as we already discussed, that here current is increasing, so di by dt should be decreasing in the first region. In the first region, di by dt should be decreasing, or current as a whole should decrease, and that is the behavior we find here in the option A, that initially current is decreasing, so di by dt is negative, and if it is negative, then induced potential will be positive. That is the behavior of the first region in the induced potential graph. So option A will be the right answer here. Now, some of you might get also confused that how we will explain this reason and what is the explanation of this reason. So let me also clear that. First, let me clear all the reasons here. Okay. Now let's come to this point. Suppose this is point C. Now at this point, induced EMF is 0. If induced EMF is 0, it means from this relation of the potential, this is a relation for induced EMF, and then this EMF will be 0 when di by dt is 0, or we can say I becomes constant. If I becomes constant, then induced EMF will be 0. And let me zoom here. Now, at this region, in this region, we can see that current is stationary. There is no change in current, although it seems to be 0, but it necessarily not to it does not necessarily need to be 0. If it is constant, if current is constant in this region, then here di by dt will be 0 and potential will become 0. So this point this here, this region represents the point C here. These are the two connected points here. Now coming to the this region, this part of the curve, here current is increasing, so di by dt will be positive and induced EMF is minus C, minus constant time di by dt, so induced EMF will be negative, and we can see that induced EMF drops here, and after that it becomes constant. After this there is a straight line, means di dt is constant and increasing, so induced EMF becomes positive. So that's how you can explain this whole graph. And starting from this point, suppose this is point A to point C, this is point A to point C, we have this is the variation of the potential between point A and C. Initially our increase is higher, rate of fall of current is higher, or di by dt is higher, so we are getting higher potential. After that curve start to drop, or the di by dt rate or the rate of decrease starts to decrease. That's why potential starts to decrease. That's how you can explain this graph. So hopefully this is enough to explain this one. Now let's move to the next question. A coil is suspended in uniform magnetic field with the plane of the coil parallel to magnetic lines of the force. So we can say, if this is our coil, then its plane is parallel to magnetic field lines, means magnetic field lines are passing like this. So we can say area vector of the coil is perpendicular to magnetic field lines. When a current passes through the coil, it starts oscillating. It is very difficult to stop, but if an aluminum plate is placed near the coil, it stops. This is due to. Now let's first find out that why there is oscillations. As mentioned in the question, that uh, if current is passed through this coil, then it start to oscillate and it becomes very difficult to stop. So first we have to understand why there will be oscillations. So if there is a current in this loop, means it will act as a magnetic dipole, and if it acts as magnetic dipole, there will be torque acting on it, and torque is given by m cross p. Now here magnetic field is in x direction and magnetic dipole in the movement in the y direction, means angle between m and b is 90 degree, so there will be a torque acting on it, and that torque will be mb sine 90 or mb, or we can say simply that there will be some torque acting on this dipole. So let me now make some changes so that I can simply, I'm just moving the field so that I can rotate it. So now there will be a torque acting on this coil, and torque will try to rotate it in the stable condition. What is the stable condition? In stable condition, theta is 0 degree when torque is 0. So our torque will be acting such that this direction of m becomes same as per direction of the b. This is magnetic field and this is m. Torque will act such that m and b becomes orient in the same direction. So our coil will rotate. So our coil will rotate like this. Initially coil was like this, and then due to torque our coil will rotate like this. Now as it reaches to the equilibrium position, at this position this coil still has rotational inertia. So what will it do? It will slightly overshoot the original condition, and then there will be opposite torque acting on that loop, because it again want to restore it to the 0 degree angle. So initially coil was this, due to torque it comes to the equilibrium position, but due to we can say rotational inertia, rotational inertia, it overshoots its 0 degree position. Then it goes some like this, goes something down, and then again opposite torque start acting on it. Then it again bounces back to 0 degree condition, and again due to rotational inertia, it just overshoots that 0 degree condition, and it keeps on oscillating like this. It keeps on oscillating. And why this is happening? Because there is no friction. There is no friction to dampen this force. So this keeps on happening. And that's why it becomes very difficult to stop this, as there is no frictional force acting on this, and this torque is keep on acting it on first on the downward and then again on the upward, so it keeps on oscillating like this. So that's the basic we can say movement happening here. Now what happens if we put a aluminium plate near the foil? Suppose we put a aluminium plate here. So this is our aluminium plate, which we just stacked with our uh, coil. Now what happens? Let me select it. Yes. So now when this start oscillating, what happens? That there is change in magnetic field associated with the aluminium foil, and aluminium foil is a conductor, so there will be a induced EMF induced there will be EMF induced in the aluminium foil, and that EMF will be induced such that it opposes this oscillatory motion. And when this this oscillatory motion slowly dampens out, and after some time it becomes stable. So due to we can say induced EMF, due to induced EMF, the oscillatory motion stops, and this phenomenon is known as electromagnetic damping. That induced EMF is causing motion to stop. So here option D, electromagnetic induction of the aluminium foil giving rise to electromagnetic damping. That is the, we can say, option D will be the right answer here. Now let's move to the next one. Magnetic flux through a coil of resistance 10 ohm is changed by delta phi in 0.1 second. The resulting current in the coil varies with time graph as shown. The flux we have to find out, and we have already solved this type of question, as we know that induced EMF is given by minus of d phi by dt, and as we don't have magnetic field and area here, so we cannot calculate flux directly. What we do here, we calculate that flux is equal to minus E into dt. We still don't have potential here, so we use Ohm's law. From Ohm's law, V is equal to IR, so it is minus R into I into dt is equal to d phi. Now we can integrate it, as we have I dt graph here, so integral will be just equal to area of the graph, and we have already solved it by different method in our, I think, in the previous video, I think. Let me check. I think this is the one. Yes, this was the question. Here we have solved this question by two methods, one by the area method and second by the integral method. You can watch in our previous video, it will be available as question number 16. So right now I will only use the area method to save the time. So it will be negative into R. R is 10, resistance is 10, and area of this graph is half into base, that is 0.1 into height, that is 4. So 2, 10 get cancelled, and our flux will be 2. Option C will be the right answer here. Let's move to the next question. Flux linked with a coil at any instant t is given by this equation. Induced EMF we have to find out. So induced EMF is given by d phi by dt with negative sign. So it will be negative 20t minus 50 plus 0, and we have to find it at t is equal to 3. So it will be minus 20 into 6, 3 minus 50. So 60 minus 50, that is 10. So minus 10. Option B will be the right answer here. Now let's move to the next one. So slide it down slightly. Here we have infinitely long straight wire carrying current I on side open rectangular loop of and a conductor C with sliding connector are located in the same plane as shown in the figure. The connector has a length L and resistance R. It slides on a right to the right with velocity v. Resistance of the conductor and the self-inductance of the loop are negligible. The induced current in the loop as a function of separation R between the connector and the straight wire is. So we have to find out the induced current in this closed circuit as a function of separation of this distance small r. Now we know that to find the current, we need to calculate the induced EMF in the circuit. And for induced EMF, what we need? We need magnetic field and we need area. But if we look closely here, as the distance changes from the wire, magnetic field's value is also changing, because we know magnetic field due to a infinitely long wire is given by mu naught by 4 pi into twice of I by the distance from the wire, or mu naught I by 2 pi d. As we changes the distance, value of magnetic field is also changing, and as we moving this conductor from in the right side, the area of this loop is also changing. So here both magnetic field and area both are variable. So to solve this type of question, we have to take the part of integration, and for that what we will do here, we will consider a small element. Let us consider a small element. So suppose this is our small element. Of this closed loop, we consider a small element of thickness dx at distance x from the wire. So area of this small element will be, as one of this side is dx, its thickness is dx, and its length is equal to length of the conductor L. So we can say dA, area of small element will be L dx, that's the area. And magnetic field at distance x from the wire, Bx will be mu naught 4 pi 2I by x. This is the value of the magnetic field. And now flux d phi associated with this small element, it will be B into A. So mu naught 4 pi 2Ix into L dx. This is the amount of flux associated with this element. Now we know that EMF induced is given by d phi by dt. Induced EMF is given by d phi by dt, and we already have the value of d phi. So just substituting value of d phi here, it will be mu naught by 4 pi 2I by x L dx, and we dt here. Now dx by dt is the velocity of the this we can say small element moving in the right side, or velocity of this conductor. So our induced EMF will become mu node by 4 pi into 2I x L into V, and we can write it like mu node I L V by 2 pi x. Now, normally when we find induced EMF, then we take differentiation. We take differentiation of the flux with respect to time. But when we consider it, when we calculated flux for small element, it was already differentiated. That's why it does not need to be differentiated. We simply divide it by dt. Now we have the induced EMF. What we can do right now? Now we can divide it by the resistance to calculate the current. So current will be E by R. So that will be mu node I L V by 2 pi capital R. That capital R is the resistance, and X is the distance from the wire. So the best answer our is, I think, this one, mu node by 2 pi ILV by RR. So option D will be the right answer here. Now let's move to the next one. Here we have the figure shows a square loop of side 5 centimeter which is connected to network of resistances. The whole setup is moving towards right at constant speed. At some instant, if the part of L is in uniform magnetic field of 1 Tesla perpendicular to plane of the loop, if the of L, resistance of L is 1.7, I think this should be ohm, the current in the loop at the instant will be close to. So we have to find out current in the loop. So first of all, this question consists of two parts. One is of electromagnetic induction, where we have to find the induced EMF, and second is the network of resistances. So first we will find the induced EMF, and induced EMF we know for a conductor. For a conductor, induced EMF is given by BLV, where B is the magnetic field, that is 1 Tesla, length of the conductor, that is 5 centimeters, so 5 into 10 raised to power minus 2, and velocity is 1 centimeter per second, so it will be 1 into 10 raised to power 2 minus 2, so it will be 5 into 10 raised to power minus 4, and EMF will be induced only in this part. Only in this part EMF will be induced, as for EMF to be induced, everything, length, velocity and magnetic field should be perpendicular to each other. Here magnetic field is out of the plane, length we can say, suppose that is in y direction or negative y direction depending upon the direction of the flow of the current, and velocity is in the x direction. So everything is perpendicular to each other, only then we have a potential. If either two of these is parallel, like for this part we have length and velocity parallel to each other in the same direction, so there will be no induced EMF in this part of the we can say this part of the wire. So only in this section of the wire there will be induced EMF, and the value of induced EMF is given by this relation. Now let's coming to the resistance part of the this setup. As we can see here that these 2 points are B and D are connected, so 1 by 2 and 1 by 2, this is a balanced vein bridge. So this part, this internal resistance will be neglected, and if this is neglected, we have 1 plus 1 2 ohm in parallel with 2 plus 2 4 ohm. So their combined resistance will be 1 by 2 plus 1 by 4, that will give us 4 2 1. So this will be 3 by 4 in taking inverse, 4 by 3 ohm out of this part, and we also have, it was mentioned that, yes, here it is, resistance of L, means of this loop, is 1.7 ohm. So total resistance will be 1.7 plus 4.4 by 3. 4 by 3 is 1.33. So it will be approximately 3 ohm. This will be the value of resistance. Now current will be potential by resistance. So 5 into 10 raised to power minus 4 by 3. It will be 1.67 into 10 raised to power minus 4, or 167 into 10 raised to power minus 6, 167 microampere. That closely resemble with option B, 170 microampere. So with this, I end this video here. Again, hopefully whatever we have discussed is helpful to you. If you have any doubts or suggestion, you can put them in comment section. I will try to resolve them. And again, if you find this video useful, then do press the like button, share it, and subscribe to our channel. And if you want to support us financially, you can scan any of these QR code in front of your screen and donate us whatever amount you want. Any amount will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.